Hello? Hello? I'm good? Okay. Can everyone hear me? Right. Hello? Okay. Okay, that's fine. All right. Is that the regular mic?
Hello?
Cool. Okay, so I have two mics on me?
Double trouble.
All right, can everyone hear me well? Good? All right. So good morning, thanks for coming everyone. So today we're gonna be reviewing for your final for Dr. Hyder on Friday at 8 in the morning, or 7 in the morning, don't forget that. So I made this review and I just wanted to note that it's just a partial outline of everything that you should be covering. It's not absolutely everything, but it should help you focus and it should help you decide like things that you need to brush up on and focus more on in your own studies. So I was thinking that we could start on the very end, almost at the very end, towards the gases, which is where we left off kind of in class, and we can kind of get that out of the way. So a few things to note for this. I have a couple bullet points as to things that you should be remembering. So pressure, remember, the standard unit is the atmospheres, and 1 atmosphere is equal to 700 millimeters mercury, and also it's equal to 101.3 kilopascals. Just something to note.
I'm going to zoom in here for you.
Okay, thanks.
By the way, this is the knob that you zoom in.
All right.
So zoom out, zoom in.
All right, cool. So one of the things that we use to measure the difference in atmospheric pressures is called the manometer. And it's kind of this little device that measures the pressure of a gas inside the little container and the pressure of the atmosphere. And then you would just measure the distances and the height. All right? So another thing is we have temperature, density, and standard temperature and pressure. Can anybody tell me what STP is? The values for it. Thank you. Awesome. So yeah, so exactly right. We have 1 atm for pressure, and then for the temperature, it would be 0 degrees Celsius, and when we convert that to Kelvin, we just add 273. So our first question that we're presented with is to convert 85 degrees Fahrenheit to Celsius and then Kelvin. So something that we need to have is that we have Celsius is equal to the Fahrenheit temperature minus 32 times 5/9. So when we plug in our value, we have 85 degrees Celsius. We would just plug in that particular value into the equation. I'm sorry? I don't know what's up with that. I guess we'd have to just bear with that for now. I don't know why it's flashing, but hopefully it'll get resolved. So once we get that, we would get a value of 29.44 degrees Celsius. And to convert that into kelvins, we would just add 273, right? To get a final value of 302.44 kelvins. So temperature is definitely something that you want to have available to you because it will be provided on the exam. And so now we can move on to our particular gas laws. So we have a bunch of gas laws, and the names for them doesn't really particularly matter. You're never going to be asked what's Avogadro's law and then like just verbatim spit it out. What you do have to remember is the relationships that each of them have. So for Avogadro's, V1 over N1 equals V2 over N2. Can anybody tell me what kind of relationship that is? Direct or inversely related? I heard it. Directly related? All right, cool. So they're directly related, and then one thing to note is that for the volumes, the unit doesn't particularly matter as long as they both match so that they can cancel out, right? However, the value for N has to be in moles. Okay? We have Boyle's law, and pressure and volume are inversely related, so P1 V1 equals P2 V2. Just something to know, this is pressure. Charles' law, it says that V1 over T1 is equal to V2 over T2. So that tells us that they're directly related. One thing to note, though, that this temperature value should be represented in kelvins. And then we have Gay-Lussac's law, which relates pressure and temperature, and those two are also directly related. Something that actually really helps me out is that if you don't really remember any of these particular laws, the one that I would definitely stress remembering is the combined gas law, because that tells you the relationship between all of them. So one thing to note is that if the units are not mentioned, we just assume that it stays the same. Okay? Okay. So then we can flip over to the next side. Where is the next side? And that would be moving on to our ideal gases. So the ideal gas tells us how gases should behave. So the ideal gas tells us how the gases should behave in ideal conditions. Exceptions to these conditions include when the volume of the gas is substantial. And when interactions between the molecules is substantial as well. So that occurs when we have really cold temperatures, when they're moving really slowly. So something to remember is PV is equal to nRT. And this is our gas constant, right? You would never have to really memorize this as it would be provided, but take note of the units. So when we're using ideal gas laws, the volume should be in liters, pressure should be in ATMs, we should have moles, and then we should have temperature in kelvins. Okay? Yeah, so that's one of the exceptions, like one of the violations of the ideal gases. So when the volume of the gases is substantial, we're going to go down and use Vander Waals equations for real gases, which is how they behave in like actual circumstances. Okay? But we'll touch more on that in a second. And then we have Dalton's law of partial pressures, which just states that the total pressure is equal to the sum of all the individual pressures. And I don't know what's going on, but okay. I guess we just have to deal with this for now. All right. So we have the concepts of diffusion and effusion. So diffusion is the collection of molecules spreading from high concentration to low concentration, as I'm sure you guys go over great in depth in biology. Okay. I guess we'll take a break for a second.
Well-needed one.
Is it good now?
That should be good.
Awesome. Thank you. So we have diffusion and we have the concept of effusion. So the way I remember it is that effusion escapes through a tiny hole in the vacuum. So that's just that. It's kind of just a definition. And we have the rates. And so when we're using this equation, just remember that if we're using a particular gas, it has to match up on both sides of the equation. So we can never have, for example, oxygen. If we were using oxygen and the rate of nitrogen, we can never do oxygen and then nitrogen. It would have to be matching, okay? But we have more problems on that. And then Vander Waals equations, these are for the real gases. These are one of the things that will be provided to you. So I would say don't memorize, as it will be given. But just remember that these values for A and these values for B would also be given. And they would just depend on the particular gas that you're using. Okay? So let's move on to an equation, or application. So for 52, a volume of liquid is 14.3 liters with a pressure of 67.8 kilopascals, and it's compressed to a pressure of 72.3 kilopascals. So what is the new volume? So we have to remember the relationship between pressure and volume. So this represents our V1, this represents our P2, P1, and this represents our P2. So it's asking essentially for V2. So how do these variables relate? That's by Boyle's law. So Boyle's law said that P1 V1 is equal to P2 V2. So we would just plug in our values. So we have 14.3 liters times 67.8 kilopascals. And remember, like I said, the units don't really particularly matter as long as they cancel out. So we're looking for volume, and both sides use kilopascals, so that's perfectly acceptable. So in order to find V2, we would just isolate by dividing by both sides. And these units cancel out nicely so that we're left with liters. And we should get a final volume of 13.409. And if we look over to our choices, that correlates best with D. Any questions on that? Okay. So the next question is saying that we're boiling potatoes in 1.2 liters of water at 45 degrees Celsius on the stovetop for 15 minutes. Bless you. So you check the potatoes temperature 5 minutes later and decide to turn up the heat to 67 degrees Celsius. What would be the volume of the pot when you turn up the temperature? So for this one, we have to remember our relationship between volume and temperature. So that's V1 over T1 is equal to V2 over T2. So this would represent our V1, T2, and this would represent our, T1, T2, okay? So we would set this up like this, right? Is that correct? What did I have to do? Kelvin, right? So remember, degrees Celsius plus 273 is Kelvin. So when we do that, I'll replace this with a 318, and I'll replace this with a 340. So it's algebra again, we just isolate for V2. So V2 is equal to 1.2 liters times 340 Kelvin over 318 Kelvin. Those cancel out, and so we get a final volume of 1.283. So we can go to the next page. And that would be best with C. Okay. So finally, we have another one. There's 5.6 moles of nitrogen gas in a container with a pressure of 465 kilopascals at a temperature of 345 Kelvin. When the temperature is increased to 409 Kelvin, what is the new pressure due to the particles hitting each other at a faster rate? So can anybody tell me what relationship we need to use for this? Pressure in moles. Why do you say that one? Okay, awesome. That's a really good thought. So we have values for moles, we have pressure, temperature, and we also have another temperature. The thing is, I kind of tricked you in that this mole value was kind of a red herring. So this was a misleading variable. The moles never change throughout the equation, so we wouldn't use Avogadro's law for that one. For this one, we would use the relationship that relates pressure and temperature. So we have P1 over T1 is equal to P2 over T2. Okay? You have questions about that? So when we just plug in our values, we have 465 kilopascals over 345 Kelvin. It's nicely given to us in Kelvin already. And we're just looking for the new pressure. So we have 409 Kelvin times 465 kilopascals over 345 Kelvin. And this would give us a final value of 551 kilopascals. Okay? So this is a more conceptual problem. When dealing with the combined gas laws, which of the following is incorrect? So the combined gas law, again, is P1 V1 over T1, P2 V2 over T2. So going down the list, as temperature increases, pressure also increases. So we look at the values for each one. We have pressure and temperature. And is that true? No, right? Oh, it is true, sorry. We're looking for the one that's incorrect. So we go down to B. As temperature increases, volume also increases. That's true. They're directly related. But if we look down at C, as pressure increases, volume also increases. Now we know these two are inversely related, so as one goes up, the other should go down. So we know that this one is incorrect or false. Another true or false question. At standard temperature and pressure, pressure is 1 atm and temperature is 25. We kind of established that earlier. So temperature, this pressure for standard temperature and pressure is okay, but for temperature it should be 0 degrees Celsius or 273 Kelvin. So this would be false. So 57, when the volume of a container has 32.4 grams of water at a temperature of 56 degrees Celsius and an internal pressure of 1.34 atmospheres, what is the volume of the container? So for this one, we have to use our ideal gas law. And that relationship is PV equals nRT. So we have to do a couple things here. So remember, our R value is given in 0.0821. Looking back. And we have to have matching variables. So for this one, we have to have pressure in ATM, we have to have volume in liters, we have to have temperature in Kelvin, and we have to have the value for N in moles. So looking at this, we have to convert 32.4 grams of water into moles. So we do that by using our molar mass. And we know that to be 18 grams per mole. And then we would also have to convert our temperature. So our temperature would be 56 degrees Celsius plus 273. That would give us 329. And then for our pressure, it's in atmospheres, so that's good. So we're looking for volume, so we can just isolate this whole thing. So N would be equal to 32.4 grams over 18 grams. R would be 0.0821 atmospheres per liter over moles Kelvin. And our temperature, like we said, would be 329 Kelvin with a pressure of 1.34 atmospheres. So when we get our final volume, we would get 36.24 liters, but our answer choices are in milliliters, so what do we have to do? We have to multiply by a conversion factor. So we have 1,000 milliliters per liter. That would give us an answer of this. And this answer is a little bit different than the choices given here, just because of significant figures, which we'll go over in a sec. But our answer choice should be B. Any questions? Okay, cool. So 58, a gas diffuses at a rate of 1.63 compared to oxygen gas at constant temperature. What would the molar mass of the unknown gas, and what element is the molar mass closest to on the periodic table? So we have to remember how our rates of diffusion relate. So we have rate of gas A, rate of gas B is equal to the square root of the molar mass of B and the molar mass of A. So in this case, A would represent the unknown gas. So it said that the gas diffuses at a rate 1.63 compared to oxygen gas. So in comparison, it's based off of 1. So we have 1.63 over 1 is equal to this. And we know the molar mass of oxygen gas to be 32 grams per mole, because oxygen gas is one of the diatomics. And then we would just be given with the molar mass of A. So we just have to rearrange this a little bit to get our molar mass of A. And we would get 32 over 1.63 squared. And that gives us a final answer of 12.029 grams per mole. So luckily, they already have it kind of matched here. And in this case, the answer choice that would best represent this would be C, carbon. Oh, question? I'm sorry? Can you say that a little louder? Why is rate mean 1? Because in this question it says that the gas diffuses at a rate 1.63 compared to oxygen gas. So it's 1.63 greater than a standard, which we would just assume to be 1. Okay? Yeah? Are you sure? Yeah. Does that make sense? All right. So do we have any questions about the gases at all? Yeah. For 32, okay, really good question. So the question was, how did we get 32 for O2? And we have to look at this equation, and it says rate A, rate over B, is equal to the square root of molar mass of B over molar mass of A. Can anybody tell me how we find molar masses? Yeah, so you just have to know that oxygen is a diatomic atom, and so you would just look at the periodic table. One single oxygen is about 15.999 something, so you just multiply that by 2, okay? Yeah.
Would you be given in a different question the rate of B, or would you always have to kind of figure it out that one is equal to the other?
That's a really good question. Sometimes it'll give you like rate A equals this, some rate A equals this, but I just wanted to give you a sample problem of where it's a little bit trickier. Okay?
Okay, so if they don't give you, if they don't give you rate B, would you just have to assume that the rate they give you is bigger than the other rate? Therefore, you have to like what you did here, you did. Like
Yeah, one would be greater than the other. They would have, I would imagine that it would indicate that it diffuses less or diffuses greater. They'd be a little bit more clear. I just kind of made this question, so hopefully that's good. But does that answer your questions? Yeah? Awesome. So we can move on. So we're going to jump around to the page where it's about electromagnetic radiation. Okay. So here's electromagnetic radiation. Here are some things that I think are particularly useful to remember. So the speed of light, this would be given to you, so don't worry about that, but just know that it's 3 times 10 to the 8th meters per second. And we would use that in our subsequent equations. So we have the equation for frequency, which is the number of waves that pass a point during a given time. So we have V equals speed of light over lambda. And we know that when we have a greater wavelength, we have a smaller frequency. And that also means a lower energy wave. Something that I wanted to add that I forgot to was Planck's constant. And that's just 6.626 times 10 to the negative 34th joules per second, okay? We also have another relationship down here. We have the energy of a wave is E equals HV is equal to HC over lambda. And then we also have de Broglie's wavelength. So in this equation, we have lambda is equal to Planck's constant, which I set up here. And we have the mass times the velocity. So just keep in mind the units here. So when we're given the mass, we have to have it in kilograms so that we cancel it out in the constant up here. And then we have velocity in meters per second. So something to note is that if you're given, is this clear? Okay, cool. So if you're given a velocity other than the speed of light, which is just c, other than c, right? You want to use the Broglie's wavelength. So moving down, we're going to apply some of the things up here. So what is the energy of a wave that has a wavelength of 5.67 times 10 to the negative 9th meters? So one hint is that it's the speed of light and the Planck's constant are in the equation. So we're going to use this particular equation, right? So we have E equals HV equals HC over lambda. So we just plug in our particular constants. So we have 6.6 times 10 to the negative 34th joules per second times 3 to the 8th power. And then we also have what was given to us up here. So when we solve for that, we get an answer of 3.57 times 10 to the negative 17th joules. Okay. Another particular relationship that I think is useful to know is from meters to nanometers. In this case, the nanometers is the smaller unit, so we're going to have a large quantity in comparison to the meters. So we're going to have 10 or 1 to the 9th power nanometers in 1 meter. So that'll be useful when they give you wavelengths that are in nanometers and you just have to convert it to meters, okay? So moving on. Where's the next page? Yeah, Planck's constant will be given as well. So this is out of order. Where is it? Okay, they're over here. So in that particular problem, our answer should have been this guy, A. Sorry, that was like from the previous question, and the formatting was just off. So do we have any questions about that? Just plugging in stuff. So for 35, out of the following options, which of them has the lowest frequency? So we have to remember our electromagnetic spectrum. So this is a really poorly drawn wave, but it should help represent what it is. So we have radio at the very bottom. We have microwaves, infrared, visible, UV, X-rays, and gamma waves. So at the very end, we have a really long wavelength, which is represented by lambda. And in this case, we have really low energy and a small frequency. But at the very opposite end, we have a short wavelength, and we have high energy. So out of the following, which one has the lowest frequency? So we would just use this and basically just memorize it. And we would see that radio waves has the lowest frequency. Okay? So now we're going to move on to quantum numbers. And quantum numbers basically just tells you where the electrons are or how they're oriented. So this particular table would help you, it would help you kind of decipher what kind of quantum sets are appropriate. So remember that we have n, which is the principal energy level. It's the 1 in 1s. So this would just tell you the orbital number. L is just the angular quantum number, and this tells us the shape. So for S, it would be 0, P, it would be equal to 1, and D, 2, F3. And these kind of make sense because when we go down to M subscript L, which is the magnetic quantum number, this tells us the different orientations that they can take. So for instance, I'm going to take this P equals 1 value. What kind of shape do P orbitals have? Dumbbells, right? So The particular shape is given by the L value, but we know that from m subscript L, it can be whole number values from negative L to positive L. And so this would just tell us how many orientations it would have. So for p equals 1, it would have these values. And these just kind of correlate to the different orientations that it can take upon the axes. Okay? And then S, which is the quantum spin, it can only be negative, positive, or negative 1/2. So for these kind of questions, they could just ask you which of the following is appropriate for a 4s orbital, and you could just see this particular set would be okay. You could have 4, 3, negative 3, and then one of these values. So just identifying which of the following would be inappropriate for that particular set is what I would imagine the questions to be. Okay? So orbital filling, some of the rules that we have to remember is that electrons occupy the lowest energy orbitals available. So we're going to do 1s before 2s, and then you're going to fill in the following order. And this corresponds kind of to your periodic table. So we can flip over to the next page. And in this periodic table, it kind of tells you where each of the following orbitals are. So I would just have a good understanding of this, that these are the S, D, P, and F. So when we're working with orbitals, we have some set of rules to know, and I would definitely memorize these or have a good understanding of them. So we have the Pauli exclusion principle, in which no two electrons in an atom can have the same 4 quantum numbers. We have Hund's rule, which says that when filling degenerate orbitals, electrons are filled singly first with parallel spins. And then we have off-balance principle, which is that lower energy levels are filled first, and orbitals can only hold 2 electrons each. So these are kind of abstract concepts, but we'll get into them in a second. So we have electron configurations, and when writing all of the energy levels that are filled with electrons and how many in each. So we have a shorthand, which is the noble gas configuration, and that will be seen down here. But for instance, it would be like writing lithium, and we would write the nearest noble gas, and then we would just go on from there. So noble gases themselves cannot be its own abbreviation. So for instance, neon can't be abbreviated, it's just any. It'd be nice, right? So for mercury, we're going to practice a little bit. So for mercury, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and it just keeps going. All right, so we just looked at the periodic table for mercury and kind of just kept going. So when we would abbreviate this, we would go to the nearest noble gas, and in this case, it would just be xenon. And from there, we would continue. So we have 6s2, 4f14, and 5d10. Don't really have the periodic table, but you're just going to trust me on that, okay? So for 37, what is the noble gas configuration of selenium? So for selenium, the answer would be B, and that would just be confirmed by your periodic table. You would go to argon, 4s2, 3d10, and then 4p4. So we're going to draw the orbital diagrams of selenium real fast. So just going off of the residual orbitals off of argon, we're going to have 4s, we're going to have 5 for 3d, and we're going to have 3 for 4p. So remember, each orbital wants to have opposite spins. You can never have 2, but when we're filling, we're going to do parallel spins first. So should I draw an up spin or a down spin for this last one? Down spin. Stupid question. Okay. Do you have any questions on anything from this page? Okay. So we go on to the next page, and the question is, how many valence electrons are in the electron configuration for magnesium? So magnesium is an alkaline earth metal, and of these, the correct one would be D. So for 39, which of the following transitions results in absorption of the highest energy photon? So we're looking for absorption, and we're looking for highest energy photon. So when we absorb energy, the electrons are going to be excited to a higher state. So electrons absorb energy. However, when they release energy, they're going to be demoted to a lower state. So we're looking for absorption, so we're looking from lower to higher. So we know that we can cancel out some of these. We can cancel out this because it goes from 6 to 2. We can cancel out this, and we can cancel, well, that's it. So of these, which of them has the highest jump? And that would be B. Okay. The way that I look at this is that I compare the values of the changes. So this one has a +3. This one went to a +1 and a +1. So if this weren't an option and you were looking for the highest energy photon, which one absorbed the most energy, I would choose the one that started at the lower level. Because in that case, it had the largest gap. And what I mean by that is that, remember we had those diagrams in which as you go higher in energy, the energy difference didn't really change that much. So if we had a +1 from here to here would be much greater than here to here. Does that make sense? Okay. So that's just a little trick for you guys. Do you have any questions on that? So for 40, which of the following transitions results in the shortest wavelength? And remember, shortest wavelength of light, and wavelength is inversely related to energy or the frequency. So basically what it's saying is which one releases the highest energy light. So of the following, we want to figure out which one released the highest energy. So the keyword is released, and it has to go down in energy so that we know it can't be B, and it can't be D, and it can't be E. So we have to compare A and C, and of the two, the correct answer would be A, in that it had a higher gap than 4 to 3. Okay? Now we can go on to a quick summary of our periodic table trends. Do you have any questions of anything that we've done so far? Okay, cool. So this is a really useful picture that depicts all of the trends in which they increase. So we're just going to talk about them for a little bit. So electron affinity, this is the energy that's released in the process of gaining or attracting an electron. So I'll just write that really fast. Energy released in the process of gaining right? So this value is usually exothermic. An example of this would be chlorine abstracting an electron to become an anion. So the trend in which this increases is it increases up and to the right. Okay, do you have any questions on that? So moving on to the next page. We have atomic radius. And atomic radius and ionic radius are a couple of the weird ones in that they don't follow the other ones. So atomic radius increases as we go to the left and as we go down. So it increases left due to nuclear charge. In that we have due to nuclear charge decrease. In that we have less protons and less positive charge. So, and it increases down. Due to an increased number of orbitals. Questions? Okay. So for ionic radius, we have a couple of trends that we should keep in mind. So we have cations and anions. So cations are ions in which the element or atom lost an electron, so they have a positive charge because they lost an electron. And anions are negatively charged because they gained an electron. So in this case, cations are smaller than their parents, and anions are larger. So we have another trend for ionization energy, and the rest of these are going to be kind of similar in that they're going to increase up and to the right. So a little bit about ionization energy. It's that it's the energy needed to lose an electron. So these are typically in correspondence to your valence electrons. And something to note is that if you see a jump in ionization energy, it means that you depleted the valence electrons and that you're now going into your core electrons. So for example, if we were given the options of calcium, aluminum, and sodium, and we were given these particular ionization energies, we would just look for the one that had the biggest jump, okay? In which case that would be from the the second ionization energy to the third. It was about a jump of like 5,000, right? Sorry, this is bad. But in this case, we would see that after we lost the second valence electron, we started dipping into the core electrons. So we would look at the valence electrons for these based on the columns. So calcium's an alkaline earth metal, so it has 2. Aluminum has 3, and sodium has 1. Sorry, this doesn't make sense. But in this case, you would choose the one that had 2, and that would be calcium. But I think we have a subsequent problem later. Yeah? Why did I choose calcium? Really good question. So we looked at the given ionization energies, and the biggest gap was from the second ionization energy to the third ionization energy. So basically what that's saying is that when we ionized the third electron, that was part of the core electrons. So basically what these tell us is how many valence electrons the atom of interest has. With that valence electron, right. So if, for instance, this was 1,100, right, instead of 6,000, we would know that the biggest jump occurred from ionizing the third to the fourth electron. So we know that the atom would have 3 valence electrons, and the answer choice should just be aluminum instead. Does that make sense? Yeah? Okay. So moving on, do you have any other questions? So we have electronegativity, and this also increases up and to the right. So this particular trend is the ability to pull electrons. This will give rise to polarity, in which we'll practice later on. But this is a trend that relates to the polarity of bonds and whether or not there's a net dipole or no dipole at all. And then finally, we have effective nuclear charge. And the equation for that is Z effective is equal to Z minus the core electrons, or in other words, protons minus core electrons. So it increases, as I said, up and to the right. And it increases up because it gets closer to the nucleus. the outermost electrons, right? And then it increases to the right because we're going to have a greater number of protons and electrons, which increases pull of nucleus on the valence shell. Okay. So let's practice this for a second. So which of the following molecules is the most electronegative? So remember our trend for that is up and to the right. And we're going to look at each of these. So if we had a periodic table, this one's kind of bad, but if we were relating the 4 of them, we would see that the order should go oxygen's the most electronegative because it's up here. Then we have nitrogen, and then we would have sulfur and bromine. So I know these because I looked these up, but if you weren't given values, you wouldn't be able to tell because these actually oppose the trend. So we would have sulfur here. This is like a periodic table, but we'd have sulfur and then we would have bromine. And remember the trend is up and to the right, but in this case it's down and to the right. So based on this, we can't tell. But I just ordered it because I looked it up. So the correct answer for the most electronegative would be oxygen. And so for 42, we have element X has the first 3 following ionization energies. We have 610, 810, and 4,500 kilojoules per mole. So of these, the biggest jump occurred from here to here. So therefore, losing the 3rd electron kind of ate into the core, so it was part of the core. So with that being said, we can determine from these that these are your valence electrons, and so our particular atom should have 2 electrons, right? Or 2 valence electrons. And of these, we know that phosphate, based on our polyatomic ions that we should have memorized, it would be PO4 3 neg. And so we would cross them, and we would get a formula of X3 PO4 2, which corresponds to option D. That was a lot. Do we have any questions on that?
I have a question.
Yeah.
So you know that there's 3 of those, then there's 6 you just almost cross multiply?
Yeah, so this was kind of a shortcut that is really helpful for making compounds. But in this case, we would need 3 of our atoms to neutralize the charge of the phosphate, right? Because we can never have like half of atoms or anything. Does that make sense? Yeah? Any other questions? Yeah.
For like problems where they're asking if it's like polar covalent or just pure covalent or ionic, are you going to be given electronegativities? It's like, I know like some of them like beryllium chloride is polar covalent, but looking at the periodic table it looks ionic.
It looks, yeah. So there are particular values that we're going to go over in a second that you'd have to have memorized, but if they were really close like that, I would imagine that the values would have to be given to you. Otherwise, you couldn't tell. That make sense? Yeah? Okay. So moving on for a second. Okay. So we have characteristics of elements. So these kind of summarize like the most important columns in your periodic table. So the alkali metals, they're the leftmost group, and they form positive cation, positive 1. The next group is our group 2A, form a 2+ cation, and then on the other side we have halogens. These are your group 7, and they are going to abstract an electron to become a negatively charged anion, and the noble gases are the rightmost, and they already have a complete octet, so they're not really going to participate in chemical reactions. Okay? So moving on to 43, we have select which element is a metalloid. So for these questions, we're going to look at the staircase that's present in our periodic table. So our staircase is what I'm referring to is this particular staircase. So any element that kind of touches it is a metalloid. So if we're looking at option A, magnesium and calcium, those are all the way over here, and they're metals, so that doesn't make sense. If we were to skip B and go to C, we would see that these are your transition metals. They're in this category, so our correct answer should just be B. So metals form ions with, and this is kind of a poorly written question, but you just have to understand that metals usually form cations, because metals usually are going to have a greater propensity to donate the electrons. So in this case, the correct answer should be anions, because metals form cations. Okay. And then we have 45. Transition metals are located in groups 3 through 12 on the periodic table, but have unique characteristics. What makes these transition metals unique compared to other elements? And if we were to look at each of these, they have a set charge and can bond to noble gases. Remember, noble gases don't really participate, and they don't really have a set charge, so we can cancel that one out. They have a set charge and all have the same characteristics as one another. We know that not to be true. This part in particular is definitely not true, so we can cancel that out. They all have a different set of positive charges and can bond to anions. And we kind of established that metals bond to anions, and transition metals, remember, can have variable numbers of charges. So this would be the correct answer. So, now we can move down to lattice energy and Coulomb's law. So Coulomb's law, I would have this relationship memorized or understood. And another trend for lattice energy is that it increases up and to the right. And in the relationship, the Q is representative of the charges, and the R is representative of the distance between. So pictorially, we would have Q1, and this particular distance represents R, and we would have the charge of Q2. So some things to note is that the lattice energy becomes less electronegative, or less exothermic as ionic radius increases, and lattice energy becomes more exothermic as magnitude of the ionic charge increases. Okay? Do we have any questions on that? So let's move on to Lewis structures, which hopefully you're really familiar with. So these are the particular rules that we should have understood. And another one is that if an atom, or if a compound in particular has multiple resonance structures, the best would be the one that reduces formal charge overall, or the one that places the negative charge on the most electronegative atom. So some things to note is that when we're drawing ions, the cations lose electrons. They become just the element's symbol with the charge. So for instance, sodium would just be Na+, and anions gain electrons. So they're drawn as the element's symbol surrounded by valence electrons, brackets, and its charge. So in this case, we would have fluorine gaining a full octet, and it would just have a -1 charge. And then something else to note is that some can have incomplete octets, which is the case of boron trifluoride, or expanded octets with SF6. Expanded octets can only occur after the third row, because these elements can take advantage or access the available d orbital. So move on to the next page. And if we have relationships for the bond lengths. So the bond lengths are just the distances between the nuclei of the bonded atoms. And the lengths are kind of opposite of the strength. So the weaker the bond, the longer it is. So single bond, double bond, triple bond, and it decreases down that way. And these are related to the types of bond that are present in them. So remember, we only have one sigma bond all the time. And then as we go to double bonds and triple bonds, we're going to increase the number of pi bonds, which are the bonds that are above and below the particular atoms. So as I said, the relationship between them is that the shorter the length, the stronger the bond. So we'd have single bonds, like really long, double bonds, and then really short triple bonds. That helps a little bit. So 46, true or false, single bonds take the most energy to break. So as I said, the shorter the length, the stronger the bond. And in this case, single bonds have the greatest length, and they would be the easiest to break. And so this one would be false. Okay. And something to note is that sigma bonds take the most energy to break out of like sigma versus pi. But the thing is that the other two, like triple bonds and double bonds, have the additional pi bonds. So like we would need more energy to break these particular bonds. Sorry about that, but this is double. Okay. So touching a little bit into polarity, which, yeah. Okay, good question. So this was really kind of confusing, and single bonds don't take the most energy to break in that they only have one sigma bond, right? I said that single bonds are the easiest to break, but sigma bonds are the hardest to break. But the thing is that the double bonds and triple bonds also have sigma bonds, but they have additional pi bonds that you have to break as well. So that's why those take more energy. Does that make sense? So of the particular bonds, like of the bonds that make up the structures, because we have single bonds, double bonds, and triple bonds, and each of them have a sigma bond. And that particular one is harder to break than the other pi bonds that are present in the double and triple bonds, but those are still bonds, and we would still need energy to break them. So single bonds don't have those pi bonds, but the other two do. Does that make sense? Yeah? Cool. So we're going to touch a little bit into polarity, and polarity, remember, is related to the trend of electronegativity. So polarity means that one atom has a stronger pull on the electrons than the other one. Something to note is that CH bonds are never polar. And so the differences in electronegativities have to be used to determine polarity. If it can't outright be seen, or if two things are really close in polarity, I would imagine that the electronegativity values would be provided on the test. And so I would just have a little bit understanding of these. So the differences in electronegativity for nonpolar bonds would be from 0 to 0.4, polar would be from 0.5 to 1.9, and then ionic would be greater than 2. So out of the following bonds, which of the following are most polar? So remember, we can easily cancel out this one because this is never polar. And we would just have to look at our periodic table. So I'm going to sketch one out. And we have nitrogen, oxygen, and fluorine in this upper rightmost corner. And remember, electronegativity increases up and to the right. So with that being said, the trend would kind of increase diagonally. And so out of the following bonds, which is the most polar? And since these are all carbons, we have to look for the most electronegative. So of these, I would say that this bond would be the most polar, followed by this one, and followed by this one. Just because that's the way that it follows the trend of electronegativity. Make sense? Cool. So hybridization, we're going to count up the sigma bonds, lone pairs, electrons. We're going to determine the principal energy levels of the atom's valence electrons, and we're going to take the s orbital to hybridize, and we're going to take as many p orbitals and d orbitals, if applicable, needed for the same number of orbitals hybridized as sigma bonds and lone pairs. So we're going to talk about SF4. What is the electron and molecular geometry of this particular compound? So if we were to draw this out, we're going to follow our rules for Lewis structures, and we would have 6 valence electrons for a total of 34 to work with, right? And we're going to put the least electronegative in the center, and fluorine is a good giveaway in that it's the most electronegative, so sulfur should be in the center. And we're going to flank it by fluorines, draw single bonds, and then fill the octets of the outer. So we would have 2 electrons left over because we only have 32 in this particular diagram. So we're going to add them to the center. And you might be saying, you can't have an expanded octet, but sulfur is in the 3rd row, and so it can take advantage of that accessible d orbital and fill that up. So for this particular model, the electron geometry is the simpler one. It's the one where you just count the domains of electrons. So we have 1, 2, 3, 4, and 5. So what I mean by electron domains or electron groups, they can be a single bond, that counts as 1, a double bond counts as 1, a triple bond counts as 1, and a lone pair. So of these we have 5, and we know that the corresponding electron geometry should be trigonal bipyramidal. So we can cancel out C and D, but we have to look at the molecular geometry. And this one takes into account the lone pairs and the repulsion of the lone pairs. So when we add them, the lone pairs are going to want to be the most isolated. So in this particular conformation, it's going to take up a shape like this. And these bonds, the thick one just means that it's coming out to you at the paper, and the one that's dashed is that it's going into the paper. And then we would have the lone pair on its own on this side. So if we were to look at the chart that's also in this packet, we would see that if we have one single lone pair and 4 bonding electron groups, the molecular geometry would be seesaw. So the answer should be A. Do you have any questions on that? Okay. Cool. So let's go on to the next page. So what is the orbital hybridization of the following carbon attached to the carbon in the compound C2H2? So we're going to draw out our structure. And we're going to attach single bonds. And these two are going to have 2 lone pairs, in which we would just give it a triple bond. So it's talking about the carbon attached to the carbon, so it could be talking about either one of these, and they're actually identical. So of the 2, they both have 2 electron groups, and this would give us a linear molecule, but it's asking for the orbital hybridization. And something that helps me out is that I just kind of count the number of electron groups, and so of this, the answer would be sp. So if it had 3, it would be sp2. If it had 4, sp3, and so on. So the correct answer here would be B. So, do you have any questions on 49? Yeah. So the 2 electron groups, one of them would be the carbon-hydrogen bond, and the other one would be the triple bond, the whole thing. So remember I said that single bonds, double bonds, triple bonds, and lone pairs all count as 1. So we wouldn't count the individual bonds within a triple bond. Okay? We wouldn't. So this whole thing is 1, and this whole thing is 1. Right? Well, it's talking about the hybridization of this particular carbon, right? So you have to take into account the groups around it and attached to it. Does that make sense? Yeah. So in that case, we would have 2, the carbon-hydrogen bond and the triple carbon-carbon bond. Okay? So for 50, we're going to do Lewis structures. So we're going to want the molecular geometry, electron geometry, the number of sigma and pi bonds, whether or not it's polar, and the hybridizations. So that's a lot. but hopefully we'll get through it. So for this particular compound, we have 3 valence electrons for boron, and fluorines are hydrogens, so they would have 7. So we would have a total of 24. So our final structure should have 24 valence electrons, and the least electronegative would definitely be boron, and we would flank it by 3 fluorines. So we would draw single bonds to them and fill the octets of the outer. Right? And boron is one of those cases in which it can have an incomplete octet, and the bonding angles between them are 120 since there's no lone pairs. So in this case, there's definitely a dipole between boron and fluorine, but since the molecule is symmetric, we're going to have no net dipole. So electron geometry and molecular geometry would be trigonoplanar. We would only have 3 sigma bonds. Based on the cancellation of the dipoles, we would have a nonpolar molecule. And the hybridization would be sp2. Okay. Moving on, we would have HCN, and I'll just give you the structure. So it would look like this, and we would always want to consider the central atom. And nitrogen is more polar than carbon, so there would be a dipole here. So since there's no lone pairs around the carbon, we would say that the electron and molecular geometry would be linear, and the bonding angle would be about 180. So in this case, everything that's bonded has a single sigma bond. So there are 2 present, but the other 2 that's present in the triple bond has 2 pi bonds. We would say that this molecule is polar. So you would have a greater density of electrons here, and a lesser here. And then the hybridization for this particular molecule would be sp. So we have H2PO4, NH2 neg, and so this particular compound has 5 plus 2 plus 1. So it should have 8 electrons total. So for this compound, hydrogens never go in the center, and we would have 2 lone pairs. So in this case, the electron geometry would be tetrahedral, since there's 4 electron groups, but these lone pairs kind of complicate things. So if we were to look at it in a different way, I would draw it like this. And it's a tetrahedral, so the bonding angles are a little less than, they're a little less than 109.5. And so the dipoles would be attracted to the more electronegative atom, which in this case is nitrogen. So we would have a net dipole going this way. And so we would count up the bonds, and there would be, so the molecular geometry in this case would be bent. And we would count up the bonds, and we would see that we have 2 sigma bonds. It would be a polar molecule, and the hybridization would just be sp3, just by counting the electron groups. Okay. So finally we have H2PO4. I'll just give this to you again because it's complex. So this is our molecule. The least electronegative would be phosphorus, so we would put that in the center. And we would fill the octets of the outer ones first. Phosphorus is one of those that can have a expanded octet because it's after the d orbital. And so we're going to look at the geometries of 2 different molecules, the phosphorus and the oxygens. So for this phosphorus, the electron and the molecular geometry would be tetrahedral. Around this particular set, we would have 4 sigma bonds, and we would have 1 pi bond. And then we would have sp3. So although there's like dipoles around each of these, resonance kind of complicates this because the double bond can kind of hop around. So resonance causes variation in polarity. So we can't really tell. And for this particular molecule, it's similar to the NH2 anion. And so the electron geometry would be tetrahedral. And the molecular geometry would be bent. And I'm sorry, I forgot these two other sigma bonds. So this whole overall molecule would have 6. Okay. Cool. So for this next one, C2O4 2 neg, we would put the least electronegative in the center, flanked by the oxygens. Sorry. And we would attach single bonds, right? So we're going to fill the out ones first. But we already used up all of our electrons. So in this case, we're going to donate some from the oxygens and make double bonds. And so I'll just take some from here and put it here, and take some from here and put it here. So in this case, we have negative charges on these oxygens, and that would give us a polarity dipole of that. So there would be a net dipole in this direction on this side. So if we're talking about electron and molecular geometries, it would be trigonal planar for both of the carbons. It would be an sp2 molecule, and there are actually 5 sigma bonds present and 2 pi bonds present. Yeah. Mm. Really good question. Yeah, they have separate bondings between the atoms, but I was just considering the overall bonds of the whole molecule. Okay. Yeah, so in this case, I just focused on the oxygen for the hybridization, since it's the most central one. But in terms of hybridization, or the sigma and pi bonds, they could ask you for overall structure, or they could ask you for a particular molecule and what it's bonded to. So you're right in that there are 4 bonded for the phosphorus, 4 sigma bonds and 1 pi bond, but overall there's 6 total, okay? So, do we have any questions about C2O4? Right. So why is it negative towards a single bond? So these oxygens have a formal charge of a negative, whereas these have 0. So formal charge is the valence electrons minus non-bonded minus number of bonds, right? And so since these have a negative charge, the electrons are more attracted to this side, and so this would have a net dipole that way, right? This could also have a double bond here in like the trans position, and in that case there would be opposing dipoles and they would cancel each other out. But in this case they're both on the same side, and so they're attracted to that side in particular. Okay? Yeah, the resonance causes a little bit of variation. But in this case, there's a dipole. Does that make sense? So yeah, the resonance is going to flip around and it's going to be a little bit variable, so that's why I didn't like write anything here. But in this particular conformation, it's polar. Gotcha?
But if you wrote it the other way?
It would be not polar. Yeah. Okay. So for this last one, we have xenon O4. And xenon is a noble gas that can have an expanded octet, so it looks really funky. So it can actually accommodate up to 8 bonds. And in this case, the electron and the molecular geometry would be tetrahedral. Since there are 4 electron groups, it would be sp3. And if we were to draw the molecular geometry, each of these dipoles would cancel out, so it would be nonpolar. And there are 4 sigma bonds and 4 pi bonds. Make sense? Yeah. Good question. For the hybridization? Right. So hybridization doesn't really relate to whether or not the electron or the molecular geometry. The electron molecular geometry just tell you how they're oriented based on like the lone pairs and repulsion. But for the hybridization, you just want to count them, and that simply tells you like whether it's sp, sp2, sp3. Okay. For number 4?
Yeah.
For this part, you mean? Hybridization?
Yeah, you focus on just the oxygen, right? Like, is it the overall or just oxygen?
I'm sorry.
Just overall.
Yeah. Did that answer your question? So for the sp3, I was looking at the phosphorus. But for oxygen, there are 4 electron groups as well. There's the 2 lone pairs and the 2 bonds. So that would also be sp3. Does that make sense?
Well, it could ask you.
It could ask you either one.
Ask you.
Yeah. Make sense? Cool. So let's move on to the back page, and we just have 2 more of these. So SF4 we already answered in the previous question for 48. The electron geometry was trigonobipyramidal. Sorry, thank you. So the electron geometry was trigonobipyramidal. The molecular geometry was seesaw. And I'll just draw it out again. So in this case, there would be 4 sigma bonds present, and we would count the number of electron groups. So there's 1, 2, 3, 4, 5. And so basically that correlates to sp3d. And that would be nonpolar. Oops, can't spell. Nonpolar. Okay. All right. So finally, we have iodine tetrafluoride. So we would draw single bonds to the fluorines. We would fill them up. And then we would have 2 more based on counting. So we would have 8, plus 4 times 7. Actually, this would be 7, right? So we would have a total of 35, sorry. So we would have 2 lone pairs up and down here to accommodate for that. And the electron geometry would be octahedral. The molecular geometry would be square planar. And since there are 4 groups, the hybridization would be sp3d, 2. That's well. Yeah. So it has that lone pair, right. So SF4 is nonpolar because it can kind of shift around where the lone pair is. And so the dipoles would kind of like cancel each other out. Make sense? Okay. So some things to note are that when we have isomers are just when they have differences in atom order. And when we have resonance. So differences in electron grouping. And these two things would affect whether or not we have polarity. So just in the other case where we had the, I'm going to flip over, but where we had the carbon double bonds, we could shift where those double bonds are, and those would change whether or not it's polar or not. Okay? Yeah. Okay. So I'm going to talk about this molecule. Is that okay? Okay. So actually, what's a better one? Yeah. I'm going to talk about this one. So these have negative charges up here. And we know that based on like electronegativity trends, oxygen is very electronegative compared to carbon, right? So when I'm drawing my arrows, that just means that the electrons are pulled this way because it's more electronegative. And so if we were to draw it like this instead, right, we would have dipoles drawn in this way and dipoles drawn in this way. And so you see how like the directions are kind of opposite to each other? They would cancel out in that case. That makes sense? But in this case, they kind of go in the same direction, so they kind of build on each other.
Okay, so that's what it means when you say like it depends on the resonance.
Right. Does that answer your question? Cool. All right. Do we have any questions about Lewis structures? Oh, for the last one? Sorry. So for the last one, there are 4 sigma bonds and no pi bonds. Make sense? Oh, polarity. So it's a square planar molecule, and these are all really similar in polarity, so it would be nonpolar. Make sense? Thanks for catching that. So, do we have any questions about the stuff we covered? Yeah.
For like the isomers, is that like when you get an ion and you have like a different sort of like rule or something called like electron configuration, like they have like different, like how do you?
Okay, so that's a really good question. I see. So differences in atom order. So if we were to have I'm trying to think about how to explain this. How about, I'll try that question. I don't know if I can answer this one that well.
It's like consider the following atoms or ions like ER, KR negative, SE negative, RB2 plus. How many of these species have the electron configuration, same electron configuration, AR, whereas
Okay, can I see it real fast? Yeah. I would, but I'm like attached here.
Okay.
But it's this one?
Yeah. No, it's this one.
This one.
Yeah.
All right, so I'll put it up here. So the question is, consider the following atoms or ions. So we have bromine, Kr, selenium, and Rb2+. How many of these species have the electron configuration? This one. So things can be isoelectric in that they have the same electron configuration, just based on whether or not they like lost electrons or gained electrons. So positive charges mean that they lost, negative charges mean that they gained. So if we were to look at these based on our periodic table, so we would have bromine, which is, Ar, 4s2, 3d10, and 4p5. You would just look at the other ones based on that and whether or not they match, okay? Does that answer your question? Yeah? All right, I'm gonna leave this here. So let's say we have no more questions on Lewis structures or anything. So we can go on to the very beginning of the review. And we'll touch up on like the simpler stuff. So matter is anything that has mass and occupies a given space. Atoms are subatomic particles. Molecules are two atoms held together by bonds. So this may seem really simple, but these questions might be the ones that you miss. So a hypothesis is an interpretation or explanation for an observation, and a good hypothesis is one that can be falsifiable. And we do that by using experiments, which are sets of procedures designed to test hypotheses. So we have two types of observations: qualitative, which are just descriptive, and we have quantitative, which are measurable. So for laws, they are a summary of observations, and these can't be violated, and they actually allow you to predict future observations based on them. And theories are just principles that people agree on, and they kind of explain things, but they're not set in stone. So we have states of matter in which they have fixed volume and shape; those would be solids. Fixed volume and indefinite shape; those would be liquids. Indefinite volume and shape; those would be gases. So this is just a table of matter and whether or not they're mixtures and pure substances. So pure substances, if they're made up of only one thing, they are elements. And if they're made up of two, it's a compound. For mixtures, if they're uniform throughout, they are homogeneous. And if they are not, they're heterogeneous. Sorry. So the next page. Properties. So physical changes, they're done without changing the composition of the particular atom or element. So this would be an example in which we have a change in state from solid, liquid to gas, and then we have chemical changes in which the chemical composition is changed. So example is burning or bleaching something. So a particular example is when water in the gas form becomes solid form, which type of compositional change is it undergoing? Condensation is from gas to liquid. Sublimation is from solid to gas. Vaporization is from liquid to gas. And deposition represents what this is talking about, gas to solid. So that would be our answer. For number 2, which of these following undergoes a chemical change? So we would have sublimation, which is just as we described from solid to gas. So that's just physical change. Heating a sugar into caramel. Sounds good. And then we also have mixing an acid and base, which is a neutralization reaction. So these two are actually chemical reactions in which the compound is changed. So our answer should be D. Yeah. So really good question. So whether or not it's exothermic or endothermic. So the way I like to think about that is based on the energy of the particles in that state. So when we're going from a gas to a liquid, that's a decrease in energy. So the energy had to go somewhere. So this is an exothermic reaction. It released the heat, and that's why it was able to go into a lower energy state. From solid to gas, it became more hyperactive, so it had to gain energy. So it was endothermic. In vaporization, it went from liquid to gas. It's the same principle, it was endothermic. Deposition, gas to solid. It had to lose a lot of energy. Is that good? Yeah. So this is a little bit about measurements. Just understand how to convert between these. Some of the tips that I have are that just remember that if you have a smaller unit, you should have a greater value because you can fit a greater number. You can fit a greater amount of the small unit into a larger unit. And you want to place the units in a way that they cancel if you're trying to get to a different one. So we have the definitions for accuracy, and we have the definitions of precision. And remember, these can be represented by the target board. So if you're accurate, you're hitting this spot all the time. But you can be precise but not accurate in that So this is representing accurate and precise, but if you were precise but not accurate, you'd be hitting somewhere like here or something. So when we're talking about significant figures, we have rules for the zeros. So I'll write them out to the side. So zeros that trail or lead are not significant. So in this case, these would be zeros like that or these. Now if there were a particular decimal here, that would change things up. That means that we would measure it, and that actually is. These actually would be significant, but for this case, that's not present, so these aren't significant. Zeros within significant figures are so for example, the zero that's between these significant digits would be, so this would have 5. I said trailing zeros are not significant unless we're denoting a quantity. So if it was like 80, like $8 or something, that would be significant. And remember, exact numbers have significant digits. So in the example of 4,500, if we had a decimal right there, this would have a total of 4, whereas this has a total of just 2. So calculations, when we're multiplying and dividing, we want to keep in mind that the significant digits should match the lowest number of significant figures that we have, and that when we're adding and subtracting, we want to have the lowest number of decimal places. Do you have any questions on that? I know this has been a while since like the semester, but I guess we can move on. So, a little simpler stuff. So we have atomic laws, the law of conservation of mass, which states that mass can't be created or destroyed, definite proportions in which all samples of a compound have the same proportion, multiple proportions, and atomic theory. So you can read up on that and review a little bit. So we have isotypes versus ions. Isotypes are changes in number of neutrons, and ions are changes in number of electrons. And sorry, this stuff should all be correlated to this part, but for whatever reason the formatting put it here. So we have positive ions in which they lose electrons, and we have negative in which they gain. So number 3, true or false, protons and neutrons contribute most of the mass of the atom. That would be true. So most of the mass of the atom is found in the nucleus, and the electrons don't really have any effect on the mass. So how many neutrons and protons are in the 14 carbon isotype? So this represents our mass number, and our mass number is just protons and neutrons. So in this case, we know that carbon has 6 protons, 6 electrons, and so we would just take 14 minus 6, and we would get a total of 8 neutrons. So our correct corresponding answer should be A. So Avogadro's number, something to memorize, just 6.022 times 10 to the 23rd, and it can be in 1 mole. It could be the number of number of electrons in a photon or something like that. It's just a counting principle and something to remember. So elements that make up chemical bonds, we have ionic, in which we have a nonmetal bonding to a metal. Covalents are just 2 nonmetals, and metallic bonds are 2 metals. So when we're naming, we want to, if we're naming ionic compounds, if the metal only has 1 type of cation, we're going to give the name of the cation, followed by the base anion, and replacing the suffix with "ide." And going down here, we would have the same principle in which we're naming an ionic compound that has more than 1 type of cation. So the name of the cation would go first. We would have the base anion followed by "ide" last, but we would have to include the Roman numeral. So these correspond to your, if they have more than one type of cation, these are your transition metals. And the Roman numeral denotes the charge. So an example of this would be CrBr3. We know bromine is a halogen, so it has a -1 charge. So for this to have a 3 charge, in order for us to have 3 of them, chromium should have a positive 3 charge. So the correct name should be chromium 3 bromide. Any questions? Okay. So moving on, we're going to name molecular compounds. So these ones should have a prefix on them. The only exception is when the first element has a 1. We never use mono. We just state the element plus the first element, followed by the prefix for the second element, which gets replaced with an ide. So for instance, NO2, it wouldn't be mononitrogen dioxide, it's just nitrogen dioxide. And the way that I ordered them was the way that I named them was based on the periodic table. So nitrogen comes first, so naturally it would go first, and then oxygen. So naming binary acids, we would have a hydro, followed by the name of the nonmetal, with an ic, and acid. So for instance, HI would be hydroiodic acid. Naming oxyacids. So we would have the name, and the ending of the original name will change what the suffix is. So if it was ate, it would become ic, and if it was ite, it would become us, and then followed by an acid. So for instance, we would have HNO3. Nitrate's one of those polyatomic ions that we're going to get into. As I said, it's nitrate. So the corresponding name should be nitric acid. And we would have H2SO3. This would be sulfite, and this would correspond to sulfurous acid. So this is just a list of polyatomic ions that I would have memorized. We have acetate carbonate, and you just go down. A useful tip for this is just making flashcards if you haven't already memorized these. And so we're going to go down to number 5, in which what is the correct molecular formula for cobalt 3 phosphate. So using our little cheat method from earlier, it's not actually cheating, but we would cross the charges. So if both of them have a 3 positive and a 3 negative charge, we would only need one of each to neutralize the other. So the formula should be this, and that corresponds to option B. Write out the formula for the following. So lithium has a positive 1 charge, it's an alkali metal, and nitride has a negative 3 charge. And so for this particular compound, it's ionic. And so we would perform that particular cross again, and we would get Li3N. So sulfur trioxide is between 2 nonmetals, and so this is a molecular. We would have SO3. Make sense? And then hydroiodic acid, it's a binary. Like I said, it would just be HI. So we have more naming. We have potassium sulfate. Potassium is a positive 1 charge. Yeah. So we have potassium sulfate. This particular formula would be K2SO4. Nitrous acid is an oxyacid, so it would be HNO2. Silver 2 fluoride, this is a transition metal, and fluoride has a negative 1 charge. This denotes that it has a positive 2 cation, so the particular formula would be AgF2. Number 7, what is the chemical formula for magnesium bromide? Magnesium is an alkaline earth, bromine is a halogen, so our formula would be MgBr2, so C. And I'll leave the rest for you to practice. We'll move on to calculations and conversions. So just brush up on percent composition, in which mass of the particular element is the mass of the molecular mass of the element in the compound, and the mass of the overall compound times 100. So we have theoretical yield and actual yield. Theoretical is the amount that, it's like if there were no problems that occurred in the lab, the maximum amount that we could synthesize. And actual yield is what actually occurs given all the different variables that happen in the lab. So we have percent yield, which is something I would understand, which is actual over theoretical times 100. And the limiting reagent is the one in which it, like it says, limits the product created. The excess reagent is the one that's left over. And we have the idea of molarity, which is given by capital M, which is moles over liters. We have the dilution equation, which is M1V1 equals M2V2. And we have mass-to-mass calculations for converting between mass of one element to the other. Something to note for dilutions, though, just like the gas laws, the unit doesn't matter as long as they're the same, and that they can cancel. And so for mass-to-mass calculations, we would take the grams, which would be given to us, of the element A. We would multiply by the molar mass, which is based on the periodic table. And then we would look at our balanced equation, and if it's not balanced, we would balance it, and this would give us the mole ratio. And then we would finally multiply by the molecular mass of the element B. Okay, so we're good on that. So number 9, if glucose's chemical formula is C6H12O6, what is its molecular mass? So we would just have to use our periodic table of each of the particular elements in that compound. So carbon has a molecular mass of 12.01 grams per mole, and there are 6 of them denoted by the subscript, so we would multiply it by a factor of 6. Hydrogen, there are 12 of them. This is its molar mass. And then oxygen, there are 6 of them, and it's about 16. So once we calculated all of that, we would just sum up all of them, and the final answer would be 180 grams per mole. So option B. Number 10, taking the molar mass of glucose from problem 9, how many moles would be in 125.87 grams of glucose? So we already figured out the total molecular mass of glucose to be 180 grams per mole. In this particular problem, we're looking for the moles, so we want moles on the top. That's why I set it up like this. So we would multiply the fractions, and the grams would cancel out, and we would get 0.698 moles of C6H12O6, which corresponds closest to option C. Number 11, taking the moles from question 10, how many atoms of glucose are there? And for this, we need to remember Avogadro's number. So 6.022 times 10 to the 23rd atoms. And that would give us an answer of 4.209 times 10 to the 23rd. So this corresponds to option A. So for number 12, how many moles of nitrogen gas are in 5,000 milliliter solution with a density given to be 0.765 grams per liter? So for milliliters, we need to remember that to convert, we need to multiply or divide by 1,000, and this would give us 5 liters total. So we start off with 5 liters, and we multiply by the density because that's what's given to us. So 0.765 grams per liter times 1 mole over 28.104 grams, and this would give us a final answer of 0.13653 moles. And this would correspond best with option B. So what is the percent oxygen in the compound phenol? So if we're looking for percent oxygen, we just need grams of oxygen over total grams of phenol times 100. So this is 16 grams per mole over 94.12 grams per mole. And I just did this math similar to how I did this problem. And we would multiply that by 100. And we would get a final answer of 17. Yeah? Right, so good question. So for number 12, because of sig figs, the maximum amount of sig figs that we should have is 1, right? So this would be rounded down to something like 0.1, but based on the options that I gave, that was their answer. But right, so this is density. It's a measurable value. So what do we know about quantities or known measured things? How many significant figures do they have? Does anyone know? Infinite, right? So we want to go by the lowest amount, and so since this is a measured conversion, this would have an infinite number of sig figs, so we would go by this. Is that okay? Yeah? And then finally, we have 14. A chemical equation has 23.5 grams oxygen. How many grams of CO2 are produced in this equation? Okay, so we start off with 23.5 grams O2. This is a given equation to us, but I don't know if it's balanced or not, so let's look at it. So we have C2H6O2, we have CO2 and H2. Something that should stick out is that we don't have a balanced carbon, so we have to multiply this by 2. So that fixes that problem. But we don't have the same amount of hydrogens as well, so we need to multiply that by 3 to match that. But now we have a total of 4 oxygens plus 3 oxygens. So that gives us 7 oxygens. And so something that we have to do is change this guy. But we can't have like a factor, like a uneven factor. So let's just double everything, which gives us 8 oxygens plus 6 oxygens, which would give us 14. So we can just multiply this by 7. Does that make sense? Okay. So from here, we would multiply by the molecular weight. So we have 32 grams of diatomic oxygen per mole. Based on the mole ratio, we would have 7 moles of oxygen, and we're looking for grams of CO2. So we want to use this guy. And then from here, we would multiply by the molecular weight of carbon dioxide, which is 12 plus 32, which would be 44. So per 44 grams of CO2. And that would give you your answer. Okay? So moving on. Oh, sorry. So these are all just similar problems based on that. So I'm going to touch a little bit about formulas. So empirical formulas are the lowest possible numbers of subscripts. So these are useful for your ionic compounds. And the molecular weights, like the molecular is the actual number of atoms in the molecule, and these are for your molecular compounds. So if we were to have a compound like C2H6, we wouldn't want to use the empirical formula because we would lose a lot of information based on that, so we would reuse the molecular formula. So for number 19, what is the empirical formula for C6H18N9? And what is the molecular mass of the empirical formula? So we would just simplify it to its lowest possible form, which is C2H6N3. If we were to reduce it more, it would be something like this, and this would be not okay. So the correct answer for this would be D. Okay. And then moving on, something else that we should have memorized is the solubility rules. So especially memorize the ones that have no exceptions. So your alkali metals and ammonia are always soluble. So those are useful, but I would definitely have these memorized. So representations of chemical equations. An example of this would be this guy. We would do a double cross in which we get the products FeOH3 plus NaNO3. And in this case, based on solubility rules, hydroxide is only really soluble with ammonia and alkali metals. So this would be our precipitate, and this would still be aqueous. So when we're drawing our complete ionic, we're going to separate it out. This would represent our molecular equation, but complete ionic is in which they dissociate in solution. So we have Fe3+, we would have nitrate, we would have sodium and hydroxide. Moving on to the product side, in solution, the precipitate doesn't dissolve out, so it would stay solid, and then we would have sodium and nitrate. So net ionic is one that removes spectators. Can anybody tell me what these spectators are? Yeah, really good. So they're the ions that are on both sides, and they can be removed out of consideration. So this would be the nitrate and the sodium. So our net ionic would just be Fe3+ plus hydroxide. Okay. Sorry. Yeah, so this one was, yeah. Overall, I would recommend balancing them, or else you wouldn't get a correct net ionic equation. Good question. So for 20, we're going to balance the particular equation. And in this case, we're going to want to have 2 hydrogens, so we put a 2 here. But once we do that, everything kind of checks out. We have 2 cyanide ions. We have 2 nickel, or we have 1 nickel, and then we have 1 sulfate. So everything looks good. So based on that, the coefficient should be A. So for 21, we're going to balance another equation. And we're going to look at everything in particular. So this carbon has a subscript of 2. And on this side, it only has 1 carbon. So we're going to add a 2 coefficient to the carbon dioxide. And then on this side, there's only 2 hydrogens, and this side has 4 hydrogens. So we're going to multiply this by 2. So once we do that, we're going to see that we have 4 oxygens plus 2 oxygens. So a total of, we have a total of 6 oxygens. And on this side, we have 2 plus 2. This is really confusing. But we have 2 oxygens and 2 oxygens. So we need to multiply this one by 2 to give us 6. So based on that, sorry about this, but based on that, the correct answer should be C. Good. Type of reactions, we have acid-base reactions, and the acid is the one that produces the hydrogen, and the base is the one that produces the OH. I would have your strong acids and your strong bases memorized. And a neutralization reaction is one in which we have a strong acid, strong base, reacting to produce salts and just water. And actually, whenever we have a strong acid and strong base, the net ionic equation is going to be just a proton, a hydroxide, forming water. Okay. So We're actually almost out of time, so we only have 5 minutes left in the review, in which case I'll leave that open to answer any questions. As far as the review goes, I will be posting the answer key up so you can hit the rest of your answers, but do we have any questions based on the material or any questions at all? We're good? All right. Some study tips. I guess just go over this review. I think it'll be really helpful, as well as the review that was posted as your homework, I guess. And those should be sufficient enough to prepare you. I think you all do great. And I thank you for coming to an 8 o'clock review session, and I hope that it was helpful. And if you have any questions, I'll stick around for a couple minutes for you to ask them, okay? All right, I'll see you Friday, but good luck.
Thank you.
Yep.
Tips